All right, let's look at a couple of application problems that involve vectors. The first thing we need to take note of is that a vector that represents a push or a pull is called a force vector. And when multiple forces are acting on an object, we can find the resulting force by adding the force vectors. Sometimes we also take an individual vector, force vector, and we decompose it, and we actually tear it apart into its horizontal and vertical components. And in fact, that's what we're going to do in this problem. There are two forces that are acting on this object, so let's have a look at the question. The magnitude and direction of two force vectors acting on an object are 70 pounds in that direction, so that's 70 pounds of force, and 50 pounds of force in the other direction. And we want to find the magnitude to the nearest hundredth of a pound and the direction angle, so we still have magnitude and direction that we're looking for, and we'll go to the nearest tenth of a degree of the resultant force. So of course, I'd like to draw a little diagram so we have some idea of what it is that we're actually working with. So the first force of 70 pounds is pulling in the direction of south 56 degrees east, so we're pulling down and to the right. The other one at 50 pounds of force is pulling north 72 degrees, so that's up and to the right. So I only need to draw my first and fourth quadrants, and I'm going to draw these fairly large. I always wish that I could draw them larger. I love just adding more and more information to my diagrams. A picture is worth 1,000 words. So let's see, the first one's south 56 degrees east. So we are above the sort of midpoint in the fourth quadrant. And this is 70 pounds, so I can draw this one a little bit longer maybe. Let's draw it like that, and maybe we can label it with a 70 right here. And if that ends up being in our way, we'll go back in and take it out later. And then the other force, well, let's see, 56 degrees east. So this is my 56 degree angle. And I'm going to make my pen even sharper here. 56 degrees. That might be too sharp. All right, and then the other one is pulling at 50 pounds north, 72 degrees east. So that's maybe here. And this is the 72 degree angle. And that is with 50 pounds of force. Okay, so how am I supposed to add these vectors together? We're going to do just what I mentioned, is we're going to figure out the horizontal and vertical components of each of them, and then we'll add the vertical components together, we'll add the horizontal components together, and then essentially we're going to have a new ij vector. And from there we can figure out the magnitude and the direction. So let's see how this plays out. Let's even call the 70 pound vector the first one, and the 50 pound of force is being exerted. That's the second one that we were given, just in case we need to really stay organized and number them there. And for our first vector, let's try to figure out the components. So in the, let's see, how should we break this up? Since the 56 degrees is drawn in an unusual place, it's not where we normally draw our reference angle, nor is the 72 really. This will be interesting. So let me switch colors and let's break this thing down. It is moving to the right and it's moving in the downward direction. Those two vectors do make a right angle, and the horizontal component, so let's call this x1, is equal to, that's definitely equal to 70 times the sine of 56. And if you're not sure why that is, remember that the sine of 56 degrees in this case is equal to opposite over hypotenuse, which is equal to x1 over 70. And if you multiply both sides by 70, you find that x1 is equal to the hypotenuse times the sine of the angle. So if you want that in your notes, keep it in there. If you don't need it in there, then you don't have to have it. I'm going to write it from left to right, so I'm going to say that x1 is equal to 70 times the sine of 56. And let me just get oriented on my page again. I had put a number 1 up here like I was going to be working up there, and all of a sudden here I am below my diagram. So I've already started writing below my diagram. I think I'm going to stay over there and erase that number 1 up there. And then I'll keep going in here. In the vertical direction, so I'm going to call that y1, the force in that downward direction is equal to 70 times the cosine of 56. And let's get some decimal values here. I'm going to make sure that my scientific calculator is in degree mode. And it is. Great, so I'm going to type 56 and then hit the sine button. And then times 70. And I got 58.03. That seems about right. The original force was 70 pounds of force, so I've got 58 in the downward direction. Let's clear that. Type in 56, and cosine times 70 equals 39.14. All right, now I might even switch colors again. And excuse me, let's look at our second force vector. So this one is pulling to the right, and it's pulling in the upward direction. And that reminds me, up versus down in the y direction, I think maybe we should take this 39.14 and make it negative. Or we could, the calculator didn't actually return a negative value, so I don't want you to put a minus sign in front of that 39.14 and not know where it came from. So we'll just include a note later when we start combining these vectors or adding them together. We're going to make that 39.14 negative because it's pulling in the downward direction. For now, let's call this other upward vector y2. And horizontally, we have x2. And x2 is equal to 50 times the sine of that angle measure, which is 72. And y2 is equal to 50 times the cosine of 72. Let's come up with some decimals for those. 72 sine times 50 equals, I got 47.55. And I'll clear that, and 72 cosine times 50 equals, I got 15.45. Now that 72 degree angle is pretty extreme, so that 50-pound force vector is aiming pretty far to the right and not very much in the upward direction. So I'm not surprised that the horizontal component is considerably larger than the vertical component. And they're both less than 50, so that bodes well. Now let's start building our new force vector where these two are combined. I will take, so if I were you, and I should have said this earlier, I would have skipped a line in here just to help sort of separate those two processes, especially if you're not switching colors like I am. I would then skip a line in here again, especially if you're not switching colors. And I'm going to take x1 and x2 and add them together. So that is 58. I have to turn my calculator on first. 58.03. Make sure I'm adding the right values together, plus 47.55, and I got 105.58. I'll clear that and add my y values together, except in this case, I'm going to write negative y1 plus y2 equals. And again, the y1, I'm making it negative here because it's pulling in the downward direction. If you'd like to write a little note, making this negative because y1 is pulling in the downward direction. That's what I would write in my notes. You can phrase it however you want, whatever's going to make the most sense to you when you look at this example again later in your notes. So we have, let's see, y1 was 39.14, and then I'll hit this little plus or minus button in the bottom right corner of my calculator to make it negative, and then I will hit plus. My y2 value is 15.45. Excuse me, and I've got negative 23.69. Which makes some sense because the y1 force vector is pulling down with more force than the y2 vector is pulling up. So the resultant force in the vertical direction is in the negative direction, or in the downward direction. Okay, if we wanted to, and it's not a bad idea, we could draw this resulting force vector. If there were room on my diagram, I think I would draw it on my diagram. I might just draw a new diagram specifically for this vector. It's pulling to the right at 105. It's pulling down at 23.69. You could label those. And the resulting vector, let's see if I can draw this fairly well. There we go. It's pulling in that direction. Let's call this vector v. The magnitude of v can be found by taking the square root of the sum of the squares. So we have 105.58 squared plus negative 23.69. We have to square that also, and that is equal to, so I'm in my scientific calculator still. I'm doing all of this in my scientific because my students are only allowed to use their scientific calculator on this next exam that's on this material. So I'm trying to practice with the correct tool that I'll be using during the exam. So I typed in 105.58 and I'm hitting the x squared button, and I got 11,000 and change. And then I'm hitting plus. I'm not going to type the negative sign on the 23.69 because I'm squaring it. I know it's going to become positive anyway. So I've already hit the plus button on my calculator. Now I'll type in 23.69. I'll hit the x squared button, and what you're seeing on the screen now, 561.2161, that's only 23.69 squared. Now I have to hit the equal sign so that it adds these two values together, and I got 11,708.3525. I'm now going to hit the square root button, and I got 108.21. The original problem said find the magnitude to the nearest hundredth. Excuse me, nearest hundredth. So let's go with, 108.21. And that's pounds of force. I'm putting a box around that because that's actually part of my final answer. And the direction angle needs to be dropping us into the fourth quadrant. If you can, if it'll fit in there, you could put in a theta. And I will note that the theta value is equal to the inverse tan of opposite over adjacent, which is the negative 23.69 divided by the 105.58. Let's see what we get for an angle measure there. Still in degree mode? Yep. Okay, so 23.69. I'll hit the little plus or minus button in the top right corner so that I can see the negative on my screen. Then divided by 105.58 equals, I've got negative 0.2243, and then I will hit second and tangent, and I got negative 12.6. I think we wanted the angle measured just to the nearest tenth of a degree, yep. So I'm going to go with negative 12.6. Now that is a negative angle measure. If this were a multiple choice question, maybe a negative angle measure wouldn't be listed and you would need to add 360 degrees to this angle. It's also possible that since the original directions were given to us in bearing notation, that we should be answering our direction angle here using bearings, and we could definitely do that since theta is equal to negative 12.6. If you look at this last diagram that we drew just below where I am here in the corner, this angle measure right here is equal to 90 minus theta, which in this particular problem, now our theta value, we've listed it as a negative 12.6, so be careful there. I'm going to do 90 minus positive 12.6 in order to figure out what that actual angle measure is. And I got 77.4. And if we use, that's the angle measure that we would want to use in order to give our direction using bearings. So that would be south 77.4 degrees turned toward east. So this is an alternate for this as a direction angle. Quite the problem, okay? But you definitely have the skills that you need in order to do this. It just takes a little bit of practice. The unfortunate part, of course, is that you need to go looking for problems that have two different force vectors and are asking you to determine the resultant force by first tearing them apart, adding together the correct components, and then rebuilding that final force vector like we did down here. But if you stay really organized about it, if you draw your diagrams large enough that you can actually fill in some information in them, those diagrams can just sit there retaining more and more information for you so that you don't have to hold that kind of stuff in your head. Using really good labels like we did with x1, y1, x2, y2 can be helpful to keep you organized. Skipping a line while you're writing out your work would be good. You also have to know yourself in terms of whether you should be using a lined paper or if you prefer using unlined paper or graph paper for the purposes of drawing these graphs and diagrams. So you got to figure out what works well for you. All right, so let's go into our second example problem here in this applied section. Here we go. So I was thinking about working out this problem, and then I realized that there's also this one. And I think that we should start this one, or start with this one, because the diagram has already been given to us. That'll also make the problem a little bit shorter, because I won't have to draw a diagram. It will also make the problem more legible, because I won't have to draw the diagram. And then you can try the one above, and I will work out a solution for that one so that you can try that one. So for starters, what we have is here there's some kind of a crate or a box that's on a ramp, and you can see that there's a rope over here that's trying to pull that box up the ramp, or maybe just be able to keep it stationary. And this problem tells us that BC, which is pulling perpendicular to the ramp, which is interesting. There's BC. BC is perpendicular to the surface of the ramp, and there's 95 pounds worth of force being exerted in that direction. And we want to find out BA, which is the weight of the box. and then ultimately the amount of force needed in order to pull the box, excuse me, which sort of up the ramp. And so notice that AC right here is pulling in the same direction as this vector BF that's sort of aiming up the ramp, and that's aiming in the same direction as this rope. So that's why we're trying to find that, because that's the amount of force that'll be needed to keep the box stationary on the ramp. We don't want it getting away from us. So how do we find first the measure of BA? I like to take a very diagrammatic approach to this and really just stick with the basics. I'm looking for BA, which is the hypotenuse of this blue and red triangle that we're seeing down here. And I know that BC is equal to 95, so let's see, you could redraw this triangle exactly as it's oriented. So we could draw it down here, and here, and here, and just kind of close it up. We could even put in this little right angle. I would put the 95 on BC because we're told that measure, and BA is what we're looking for over here. And we've got our 18 degrees. Well, the 95 is the adjacent side length, and the BA is the hypotenuse. What trig function involves the adjacent side and the hypotenuse? Well, that's the sine or the cosine function. So I would come over here and write that the cosine of 18 degrees is equal to adjacent, which is 95, divided by hypotenuse, which is the BA. I'm looking for BA. All I have to do is solve this equation. Multiply both sides by BA. Then divide both sides by the cosine of 18. Even with atrocious handwriting, even I can do this problem. I didn't use any r cosine theta, r sine theta kind of stuff. I didn't have to convert anything into polar form. This is really very much going back to the first 3 weeks maybe of the course and the very early videos for this course, just going back to the basics. This is SOHCAHTOA stuff right here. So let's jump into the calculator and actually figure out what BA is. And knowing how to type this into your calculator is important, so I cleared my calculator. I confirmed that I'm in degree mode. I'm going to type 95 divided by, and here's where it's tricky. Now I type 18, then hit cosine, then hit equals. And I got 99.8889. So 99, let's go with 99.9. Does that make sense? Well, if it's the hypotenuse of the triangle, it should be the longest side length, and the other side length was 95. That was the one that we knew, and that's smaller than 99.9, so that's good. Does it make sense that they're really similar to each other? It does, because that 18-degree angle measure that's a pretty narrow angle, so they're almost both pulling in the same direction. Almost. Okay, so somewhat reasonable. Now, in order to find AC, and I'm going to draw that onto my diagram also, how do you think we're going to go about finding AC? I would be willing to bet that it's going to look a lot like this, except it's going to involve the sine function. You can set it up like this if you want, so that you can confirm that, and that's not a bad idea. Sine is opposite over hypotenuse, so that's AC over BA. We know BA now, so would that be a good idea? We could sort of reuse that value in order to find AC. Absolutely. Or, since we know the measure of the 95, I'm assuming it's pounds of force, and we're looking for AC, we could use the tangent function, which is opposite over adjacent. And I like that because the 95 is an exact value. The 99.9 is a rounded value. So I think I'm going to use the tangent function. So let's take it from the top. The tangent of 18 degrees is equal to opposite over adjacent. So the opposite is the AC, adjacent is the 95. And then, oh, that's nice. All I have to do is multiply both sides by 95. And I will be able to find the measure of AC. Let's type this into the calculator. Clearing my screen, I'm going to take it from right to left. I'm going to type the 18 and then hit the tangent button. I've got 0.3249, and then I will do times 95 equals. And I got 30 point, let's round it to the tenths place again. I'm going with 30.9. And these are our two solutions. We didn't have to combine anything. We didn't have to find any direction angles. The direction angle was sort of given to us already. But the value of this problem, I think there are a couple of key takeaways in this one. One is the value, again, of the diagram. It's possible that you'll have to, well, as a matter of fact, in the problem that's above this one, you would have to draw your own diagram. It's not given to you. And the angle measure that's given to you in the problem above is this angle. It's the inclination of the ramp. And you'll need to be able to translate that into the rest of the diagram. Notice where the 18 then appears up here. Try to burn the image of this diagram into your mind or redraw it without it looking quite so fancy, and get that to stick in your mind, because that needs to be a template that you're going to use for future problems of this type. Also, a little note for you is that my guess is that BC would be referred to as the normal force. And it's called, it's called the normal force because normal forces are typically perpendicular to the direction of motion, which is the case here. I mean, the box wants to slide sort of either up or down that ramp, and BC is definitely perpendicular to that direction of motion. So you might see that referred to as a normal force. BA is the force due to gravity because it's pulling in the downward direction. In this problem also, we were given BC as the known value. However, BA could be given to you as the known value, AC could be given to you as the known value, but for the most part, you're always going to get that angle measure. So stay fluid and realize that in this problem, we used cosine and tangent in order to help us find our answers. We really went back to the basics on SOHCAHTOA kind of stuff. You might need to use the sine function in a different problem depending on the information that's given to you. I'm going to pause real quick and come up with a couple of solutions for you for the problem above this one, and that way you'll have a target. I'm not going to show my work on it. I want you to try to do your own work, and I'm just going to give you sort of an answer key. So let me come up with those real quick. Okay, so in the I just paused and went up and worked out the problem above, and then I'm coming back to you to let you know that in that problem, I don't want to slide up now because I've got all my work up there and I don't want you to see that. The question above has a barrel on a ramp, and it wants to know the amount of force required to keep the barrel stationary on the ramp, essentially. What that means is that the problem above is looking for this value. So you'll need to draw your diagram, and you'll need to label put the given information in the correct locations on the diagram. The other interesting thing about the problem above is that you're going to be told that the weight of the box, or the barrel in the above problem, is, I think it was 280 pounds. Where on the triangle, this ABC triangle that we're seeing here, where does that 280 go? Well, since it's the weight of the box, and weight is typically a reference to, or in reference to, the pull of gravity, that's going to be in the downward direction. So in this diagram, it would be labeled as BA, and the magnitude of vector BA would be 280 pounds in the above problem. I've already said more than I want to, because I do want you to struggle with that one a little bit and try to find your way around it. The only thing that you're looking for in the above problem, however, is the value essentially of AC, the vector that's aiming up the ramp, and the value that I got for that is 60.6 pounds, right at the top of the screen, 60.6. See if that's what you get, and if you're one of my students and you have any questions on that one, you can let me know in class. If you're not one of my students, I hope that this video has been helpful to you and that you will join me in the future for another lesson. My students can click below me if you want to jump right to the next section video. And I thank you again for joining me. See you around.